discussion. We want to find the eigenvalues and the eigenvectors, and hence we diagonalize a 3 by 3 matrix. In our previous discussion, we found the eigenvalues and the eigenvectors for a 2 by 2 matrix. In this discussion, we want to find the eigenvalues and the eigenvectors for a 3 by 3 matrix. And we go straight to our solution. Let's start with eigenvalues. And we know that the solution to the determinant of A minus lambda times the identity matrix, which is always equal to 0. The solution to this will give us the eigenvalues. Now, this is our A. Our A is 2, 0, 0, 4, 2, 2, negative 2, 0, 1, minus lambda times the identity matrix for a 3 by 3 matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now we find that lambda times identity matrix. So let's have 2, 0, 0, 4, 2, 2, and negative 2, 0, 1. Minus the identity matrix times lambda. So lambda times 1 is lambda. Lambda times 0 is 0. Lambda times 0 is 0. Lambda times 0 is 0. Lambda times 1 is lambda. Lambda times 0 is 0. Lambda times 0 is 0. Lambda times 0 is 0. Lambda times 1 is lambda. Now we have, this is our A. This is our lambda times the identity matrix. Now we find A minus lambda times identity matrix. It will be 2 minus lambda, which is equal to 2 minus lambda. Then we have 0 minus 0 is 0. 0 minus 0 is 0. We have 0, 0. Then here we have 4 minus 0, which is 4. We have 2 minus lambda, which is 2 minus lambda. We have 2 minus 0, which is 2. Then here we have minus 2 minus 0, which is 2. Here we have 0 minus 0 minus 0, which is 0. Then 1 minus lambda, which is 1 minus lambda. Then we find the determinant and equate it to 0. Now we want to find the determinant of 2 minus lambda, 0, 0, 4, 2 minus lambda, 2, negative 2, 0, 1 minus lambda. Now we find the determinant of this matrix, then we equate it to 0. We realize that we equate it to 0 since it is not invertible. Now the determinant is always equal to 0. Now to find the determinant, we take 2 minus lambda into, we cross the row and the column, then we pick 2 minus lambda, 0, 2, 1 minus lambda. Then we pick 0 minus 0 into, we cross the row and the column, we remain with 4 minus 2 and 2, 1 minus lambda. Then plus 0 into, we cross the row and the column, we remain with the 4 minus 2 and the 2 minus lambda, 0. We realize that when we solve this, we will get 0 because we have 0 times what is inside, 0 times what is inside, which is 0. So let's focus on this. We have 2 minus lambda into 2 minus lambda, 2, 0, 1 minus lambda. Now we have 2 minus lambda times 1 minus lambda minus 2 times 0, which is 0. So the outside we have 2 minus lambda into 2 minus lambda times 1 minus lambda minus 0. So let's expand the inside part. Let's have 2 into 1 minus lambda, then minus lambda into 1 minus lambda. So we have 2 minus 2 lambda minus lambda plus lambda squared. So let's collect the like terms. We have 2 minus 2 minus 1 is minus 3 lambda plus lambda squared. And these we multiply by 2 minus lambda. So we have 2 into 2 minus 3 lambda plus lambda squared. Then we have minus lambda into 2 minus 3 lambda plus lambda squared. So 2 by 2 is 4. 2 by minus 3 is minus 6 lambda. 2 by 2 is plus 2 lambda squared. Minus lambda times 2 is minus 2 lambda. Minus 2 times minus 3 lambda is now plus 3 lambda squared. Then minus 3 times plus lambda, which is minus lambda power 3. And you should remember it's equal to 0. Now let's pick the like term starting with lambda cubed. So we have lambda cubed, it's minus lambda cubed. Then we have 2 lambda squared plus 3 lambda squared, which is plus 5 lambda squared. Then we have 3 plus 2 is 5. Then we have minus 6 lambda minus 2 lambda, which is minus 8 lambda. Then we have 4 plus 4, which is equal to 0. So realize we have minus lambda cubed plus 5 lambda minus 8 lambda plus 4 is equal to 0. Now we want to solve this solution. Let's find numbers that can divide 4. Numbers that can divide 4. We have 1 without a remainder. We have 1, we have 2, and we have 4. Now let's put 1 into the equation. We'll find that 1 will give us 0. If you substitute 1 here, it will give us 0. Therefore, using 1 into, we have negative 1, there we have 5, we have negative 8, and we have 4. Now we drop negative 1 down. 1 times negative 1 is negative 1. 5 minus 1 is 4. Then we have 1 times 4 is 4. Minus 8 plus 4 is minus 4. Then you have 1 times minus 4 is minus 4. 4 plus minus 4 is 0. So we realize that our first lambda is 1, because when you get 1, it will give us 0. So we have lambda minus 1. Since our first lambda is 1, lambda minus 1 is equal to 0, therefore lambda is equal to 1 into, we have negative 1 lambda squared, we have plus 4 lambda, then we have minus 4. This which will equate to 0. Now let's multiply across the inner part by a negative. We have lambda minus 1 into negative, it will be now lambda squared, by negative it will be minus 4 lambda, by negative it will be plus 4, and it's equal to 0. Now let's look for two numbers. When we add, we find negative 2. When we multiply, we find positive 4. That's negative 2 and negative 2. Since negative 2 plus negative 2 is negative 4, negative 2 times negative 2 is 4. So we equate, we have lambda minus 1 into, now we have lambda squared, equate now minus 2 lambda plus 4 should give us 0. Now we factorize, we have lambda minus 1 into, we have lambda into lambda minus 2, then we have minus 2 into lambda minus 2 should give us 0. So we have lambda minus 1, we pick lambda minus 2, lambda minus 2 is equal to 0. Now we realize lambda 1 is equal, lambda minus 1 is equal to 0, meaning lambda 1 is equal to 1. Lambda minus 2 is equal to 0, meaning lambda 2 is equal to 2. And lambda minus 2 is also equal to 0, meaning lambda 3 is equal to 2. These are our eigenvalues for A. Let's go ahead and find the eigenvectors. I want to find the eigenvectors now. Now, remember we add, so lambda 1 which is equal to 1 should give us eigenvector which is eigen 1 which is unknown. Now using 2 minus lambda, using A minus lambda times identity matrix which is 2 minus lambda 0 0, we add 4, 2 minus lambda 2, we add negative 2, 0, 1 minus lambda. Now our lambda is 1. So 2 minus 1 is 1, 0, 0, 4, 2 minus 1 is 1, 2, negative 2, 0, 1 minus 1 is 0. Now how do we find our eigenvectors? We perform a row reduction. We want to perform a row operation, double REF, in order to get our eigenvectors. Since we have 1, 0, 0, 4, 1, 2, and negative 2, 0, 0, we add 0, 0 on the right and perform a row operation. Let's have negative a half R, negative a half, or let's have a half row 3, and our answer we put it to row 3. Now we maintain row 1 which is 1, 0, 0, 0, we maintain row 2, which is 4, 1, 2, 0. Then half of negative 2 is negative 1, 0, 0, 0. Let's have row 1 plus row 3 and our answer to row 3. We maintain row 1, 1, 0, 0, 0. We maintain row 2, 4, 1, 2, 0. And remember we have row 1 plus row 2, row 3. So 1 plus minus 1 is 0 and the others are 0, 0. Let's have negative 4 row 1 plus row 2, our answer to row 2. So we maintain row 1, 1, 0, 0, 0. Then negative 4 times 1 is negative 4. Negative 4 plus 4 is 0. Negative 4 times 0 is 0. 0 plus 1 is 1. Negative 4 times 0 is 0. 0 plus 2 is 2. Negative 4 times 0 is 0. 0 plus 0 is 0. Then we have 0, 0, 0, 0. Now from row 1, we realize that x1 is equal to 0. From row 2, we realize that x2 plus 2x3 is equal to 0. Meaning x2 is equal to minus 2x3 and x3 is x3. So we have x1 which is 0, x2 which is minus 2, x3 and x3. Let's factor out x3. So we have x3 into 0 minus 2, 1. Now we realize that our eigenvector v1 is equal to 0, negative 2, 1. Our eigenvector 1, v1, our eigenvector 1 for eigenvalue lambda 1, which is 1, will give us 0, negative 2, 1. Let's find the eigenvector for lambda 2, which is 2. Now, lambda 2, which is equal to 2, and we realize it's also the same as lambda 3, which is 2, will give us eigenvector 2, which is equal to unknown. We use lambda, we use A minus lambda times the identity matrix, which will be 2 minus lambda 0, 0. Realize how we did it. We have 4, 2 minus lambda 2, then negative 2, 0, 1 minus lambda. Our lambda is now 2. So where there is lambda, we equate 2. So it will be equal to 2 minus 2 is 0. The others are 0, 0. Then 4, 2 minus lambda is 0 because lambda is 2. Then we have 2. Then we have minus 2. We have 0. 1 minus lambda, 1 minus 2 is minus 1. Now, how do we get our eigenvectors? We perform a row reduction just as we did. So we have 0, 0, 0, 4, 0, 2, and negative 2, 0, negative 1. So we add 0, 0 on the right and perform a row operation. Now let's have a half row 2. Our answer to row 2. So we maintain row 1, 0, 0, 0, 0. Half of 4 is 2. Half of 0 is 0. Half of 2 is 1. Then we have 0, we have negative 2, we have 0, negative 1, 0. Let's have row 2 plus row 3 and our answer to row 3. Let's have row 2 plus row 3 and our answer to row 3. So we maintain row 1, 0, 0, 0, 0. We maintain row 2, 2, 0, 1, 0. And we have row 2 plus row 3. 2 plus minus 2 is 0. 0 plus 0 is 0. 1 plus minus 1 is 0. And 0 plus 0 is 0. Now from our row 2, we realize that 2x1 plus x3 is equal to 0. Meaning our 2x1 is equal to negative x3. Therefore, x1 is equal to negative half x3. Let's have this our eigenvector 1, which is equal to 0, negative 2, 1. And our x2 is x2, our x3 is x3. Therefore, we have negative half. Let's solve it down here. We have negative half x3, negative half x3, x2 is x2, and x3 is x3. Let's factor out x3 over 2. Let's factor out x3 over 2. So, since we have x3, it will be negative 1. It is x2, it will be 0. x3 will be now 2. Plus, let's factor out x2. When you factor out x2, it will be 0. Don't have x2, it will be 1. And here, it will be 0. Now we realize that our eigenvector 2 is equal to negative 1, 0, 2. Our eigenvector 3 is equal to 0, 1, 0. Now we have solved our eigenvalues. We now have our eigenvectors, that is eigenvector of 1, eigenvector of lambda 2, and eigenvector of lambda 3. Now let's diagonalize. First, let's see if we can diagonalize matrix A. Let's see if we can diagonalize matrix A. To diagonalize, we should realize, let's start the eigenspace of lambda 1 has got a basis which is equal to basis of lambda 1 was 0, negative 2, 1. We realize the dimension is 1 and it's equal to the multiplicity of our lambda 1, which was lambda 1 was 1. It's equal to multiplicity, which is also equal to 1. That's true. Eigenvector, eigenspace of lambda 2 has got a basis equal to, the basis for lambda 2 is negative 1, 0, 2, and 0, 1, 0. We realize the dimension is now 2, and it's equal to the multiplicity, which was 2. We have 2. Lambda 2 and lambda 3 are 2, so the multiplicity is 2. Meaning we can diagonalize matrix A. Now, from our last discussion, we realize that diagonalizing just means putting the eigenvectors in the diagonal. Diagonalizing. So we were told to diagonalize. Therefore, our final answer now will be to diagonalize. We have got lambda 1 was 1, put 0, 0. Then we have 0. Lambda 2 was 2, 0, 0, 0, 2. Now we realize this, let's give it B. We realize that to diagonalize, we only put the eigenvalues on the diagonalize. Maybe you can be asked to verify. So to verify, you'll know that when you take our P times this B times P inverse will give us matrix A. And what I didn't mention earlier was that it is diagonalizable with the matrix P. It is diagonal with the matrix P equal to the eigenvectors, which is 0, negative 2, 1, negative 1, 0, 2, and 0, 1, 0. So this is our P. Now to verify, P times B times the P inverse will give us A. Thank you for watching. Subscribe, like, and share.